Today, we present Doppler correspondence, non-iterative scan matching with Doppler velocity-based correspondence. Conventionally, iterative closest point, ICP, methods perform scan matching by alternating between finding correspondences and optimizing transformation matrices. In this work, we propose a novel approach that utilizes Doppler velocity measurements from 4D scanning sensors such as FMCW radar or LiDAR, to directly estimate high-quality correspondences without iterative refinement. In short, when pointwise Doppler velocity is available, our method allows direct and reliable correspondence search in a single step. The proposed algorithm addresses the scan matching problem, which plays a critical role in LiDAR-based state estimation. LiDAR sensors, as is well known, provide precise 3D spatial measurements via laser scanning. By aligning and accumulating consecutive scans, LiDAR odometry can be computed. Due to its accuracy and robustness, LiDAR-based scan matching has been widely adopted in domains such as autonomous driving. However, in adverse conditions such as snow, fog, or environments lacking sufficient structural features, like tunnels, LiDAR-based odometry often struggles. To overcome such limitations, 4D scanning sensors like FMCW radar and LiDAR have gained traction. These sensors use phase modulation to estimate distance and operate reliably even under degraded weather conditions. Moreover, 4D scanning sensors provide not only 3D spatial information, but also radial velocity measurements, Doppler velocity, enabling potentially more robust state estimation even in feature-poor environments. Despite these advantages, Doppler information has so far only been used during transformation optimization, assuming correspondences are already given. The actual correspondence search step has largely relied on conventional nearest neighbor approaches. To address this, we introduced Doppler correspondence, which leverages Doppler velocity for direct and accurate correspondence estimation. Now, let us explain the core methodology. Suppose a 4D scanning sensor captures a scan, T. At the next timestamp, scan T+1 is obtained. In the sensor coordinate frame, these two scans appear spatially displaced. For scan matching, we define scan T as the source point cloud and scan T+1 as the target. We then draw an extension line that passes through both the source and target point. Since the target point is the result of the source point moving over time, we approximate the source's motion using a green velocity vector. Next, we drop perpendicular lines from the source point to the target's line and vice versa. Using this geometric setup, we decompose the motion vector and extract the radial component, which is precisely the Doppler velocity measurable by 4D scanning sensors. From this configuration, we identify two similar triangles, one from the sensor origin to the blue projection and another to the red projection. Using their geometric similarity, we derive a proportional relationship. The hypotenuse and adjacent in each triangle correspond to the range and Doppler-induced displacement of each point. For the blue triangle, the hypotenuse is the source point's range, and the adjacent is the target point's range minus its radial displacement. For the red triangle, the hypotenuse is the target's range, and the adjacent is the source range plus radial displacement. This yields the following equation, and this becomes the core formulation for Doppler correspondence. Let us now see how this is used in practice. We treat the left-hand side of the equation as a feature for the source point and the right-hand side as a feature for the target. If 2 points form an optimal correspondence, their features should be as close as possible. Given range and Doppler velocity for each point in a 4D scan, we compute this feature per point using the derived formula. This enables one-shot correspondence estimation and transformation optimization. By leveraging Doppler correspondence, our scan matching method achieves reliable correspondence estimation, resulting in accurate odometry. Nevertheless, some limitations remain. Between consecutive scans, the rotational motion should be small. Satisfying this condition enables the estimation of both rotation and translation. However, violating this condition may lead to degradation or failure of the proposed method. To explore its practical use, we consider two integration strategies. First, we apply a robust kernel to the optimization step. Even though our method operates in a single step, it still achieves performance comparable to or better than closest point correspondence from ICP when using robust kernels. Second, we improve performance by integrating Doppler correspondence with ICP in a hybrid scan matching approach. In summary, Doppler correspondence enables robust and accurate correspondence estimation using Doppler information, performing effectively in both structured and unstructured environments. We also analyze the occurrence of outliers under large rotations and mitigate this issue using robust kernels. Finally, the simplicity of the method allows for easy integration with other modules in 4D scan matching pipelines. Thank you.